Google I/O this year, they announced Android Jetpack, which isn't really a new thing. It's just a new term that they've kind of given an umbrella term, I guess, to all these things that they're recommending. So if you do keep up with Google, the announcement they make about Android quite regularly, a lot of the stuff that's in Android Jetpack wasn't new, but the term like Jetpack was new. And really, Jetpack is just this collection of recommended libraries and best practices and the starting point, basically. And it's separated into these 4 key areas. And all the libraries and things are kind of split up into, and again, this is all on developer.android.com. And they've all got examples and code samples and all these things. And it's just now like this is the Google recommendation. And the nice thing was it seemed like, at least they were saying, that they'd really decided what goes in this based on what the feedback they'd had from developers were. And it didn't seem like they were really set on recommending the Google way. You know, like it seemed like they could include some libraries from outside if they were just really well adopted within the community. So it's nice to see that it seems like it's going to be a bit of a back and forth evolving thing. So that's good. And then, of course, you probably have heard already. I know there's been a talk here already about Kotlin, but it's here and it's here to stay, I think. Google announced that they were officially supporting it as a language to write Android apps in last year's I/O, and it's only grown in popularity since then. They're still supporting it. They've still got all these code samples in Kotlin now, really pushing really for Kotlin to be your main language of choice, to be honest. And don't think it's going to go anywhere. And it's not Android specific either. I mean, I'm in my Android bubble. I don't know how much it's spread into the wider Java community, but it's not an Android thing. It's a language in itself, and it's completely interoperable with Java. You don't have to convert everything. You can just put little classes in, and it just works. And it's really taken off in the Android community, especially. Everyone seems to really like it and doesn't want to go back. And it's just a bit cleaner. It's got less boilerplate, and it's written. It's made by this company called JetBrains. If you want to look it up, this is another little like I/O throwback. I actually met the lead Kotlin language designer called Andrei Breslav, just walking around, and then when he left, my friend was like, "Oh, you know that was the lead Kotlin designer?" I was like, "Oh, I had no idea." But this is just one of the many opportunities that present themselves out of the blue at Google I/O. So that's kind of it, just a quick overview of Android now. If you have looked at it before, maybe it's time to look back. A lot of things have changed in the past few years, and it really seems like there is a bit more like I said, opinionated guidance from Google themselves. So there's a lot of information to be found. And also, hope I've inspired you to try and go to Google I/O. And I wish you good luck in the lottery. And you've got like a year to find a company that will sponsor you to go, because it's not cheap. But yeah, that's it. Thank you for listening. To do this.
So I think what we're going to do is give Gemma a chance to roam around and answer questions. So if anyone
have any questions, I'll be around later.
So grab Gemma during the intermission. We're going to take 5 minutes to get the next talk set up. So do grab her with any questions you got, and we'll see you back in about 5 minutes' time.
Right, we're about to start the main talk of the evening. First of all, apologies for the slight buzzing noise during the last talk. We're still trying to get used to this amazing load of equipment in the corner over there. So sorry about that. So the main speaker this evening is Cesar, who is head of engineering at Convendia. And as you know, he's here to talk about what the F is a monad. So over to you, Cesar.
Thank you. All right, thank you everyone. Thank you for having me in Brighton. It was actually my first time ever in Brighton. I had a lovely time during the day, and I hope it will continue. So talk is what the F is a monad, and I hope you understand the reference to the picture at the end. So before I start, I want to tell you why I am doing this talk. So I'm a Java developer, been doing this for maybe eight years, something like that. I started in 1.5, and up until 1.8, I really felt like something was missing from the language. And when I was looking at snippets from C#, I was like, they can do all these things, lambdas, and I want to do the same. And eventually Java 8 came up, and I was really nice. I really enjoyed the streams, the optionals, and all things like that. And I was reading an article, and that mentioned the word monad. And after reading the article, that's how I felt about monad. I just had no idea what the guy was talking about. And then, I like that sort of things, and I could really feel that functional programming is really powerful. So I decided to learn more. I got into Scala, I got into Haskell, and eventually I got into category theory, which is like the backbone, the theoretical backbone under all of it. And when I got into monad, I felt like that. So like a slight improvement, but maybe still as like there's something with this monad, but like I still don't get it. And then one day, boom, and suddenly it was clear. Like, wow, monad is so simple. And now I'm like that. I'm like getting angry, hopefully in a good way, of why people find it so difficult. And I just want to tell you a little anecdote. So in London, with the Java community, we've got this unconference every year. So we all get together, we write some talk on the board, we post it, and then we split into rooms. And I was doing one on monad, and so we went in the room, I was talking about monad, and someone came and said, oh, what is this talk? And I was like, oh, it's monad. And the guy was like, and then, like almost run. And I was like, this is why I want to do this talk, because there is nothing to be afraid of. It's really such a simple concept, and I will hopefully, a little bit later in the talk, I will try to convince you why people think it's difficult. So as a disclaimer, you might know this famous mathematician that said one does not talk about monad without mathematical rigor, and I really disagree with him. I think this is one of the reasons a lot of people are put away from learning about monad, is because a lot of the talk out there are really theoretical and trying to be exact. I do not want to do this here. I want you to remember one line in your head what a monad is, and maybe it's not going to be 100% true, but if you remember that and you want to know more, you can do it in your own time, but you're not going to be put away by some obscure details. So this is why maybe you can tell I'm quite passionate about this topic, but so why should you care? Well, I think, functional programming is getting really fashionable, or maybe it always was, and we forgot, like Lisp language, 1958. So it's not a new thing, but, languages like Scala, C#, Clojure, JavaScript, sorry, Java 8, they all have some sort of a functional aspect into them, different level. I think, from my observation, the Java community is really lagging behind in terms of function. C# introduced lambdas in 2007. Java 8 was 2014. 7 years is a huge time in our industry. I think there is little knowledge of the theoretical foundation, so if you go to a Java meetup, if you say words like Functor, applicative monad, people have no idea what you're talking about. If you go to any other meetup, Scala, Haskell, any other languages, people, they kind of like, they know what you're talking about. And I really hope that Java is going to get more functional. I mean, I think a lot of people thought Java was dead, and then Java 8 really was like, basically saved it because of the functional features. So I hope that Java is going to get more functional, and if it does, well, we might as well learn the basic foundations, the basic blocks of functional programming. So, but this is kind of like, okay, so everyone is doing it, maybe for a reason, but, this is not necessarily an absolute reason. So, but why, why is it so fashionable? Well, I think because with functional programming, you write better code. And what do I mean by better code? Well, I think strong typing, it creates robust and expressive code. So when you write small functions that have types, you look at the function and say, oh, this takes an int, returns a string. I kind of know what it does. It's really clear. All the types. I mean, the type is almost, sometimes it's 100% of the function. Sometimes for a given signature, you can only write one function that does it. And I mean, I think it's more expressive. I think it's more readable. So, you know, you're trying to break your code in smaller functions, so you don't have to understand a 1,000-line of method. I've seen that in Java. A method that does 1,000 line doesn't returns void, so those are one of side effects. So no one really knew what it does. So people were appending at the end, you know, never touching anything above, you know. It's like a log. I think immutability makes it easier to reason. So immutability is often, it comes with functional programming, it's part of the package. And if you think about it, sometimes it's hard to, if you've got a lot of mutable states, it becomes hard, oh, this process, what in these variables. But in functional programming, you only mutate in a small scope of the function. So I think it's easier to understand. Reusable code, so you're trying to always, if you see a pattern, you extract it. You see another one, you extract. So at the end, you've got these really like purely abstract functions, and I think the code is really lean. And the last one is really interesting for me. It's simple when you're familiar with it. And I got this idea when I was, so I don't know if you guys know, there is a VJUG, Virtual Java User Group, for those that don't have the chance to be in a city with a big enough Java community. And there was last year, there was a 24 hours conference. So in 3 time zones, there was every hour there was another talk. And the keynote was by Venkat, a very famous Java speaker. And he gave a talk on the art of simplicity. And it really touched me. I don't know if it's the correct word, but he showed a Chinese character on the screen, and he asked, do you think this is simple or complex? And I mean, I don't read or speak Chinese, so I was like, yeah, that seems pretty complex. But actually what the sign meant was simple. And the lesson is that simplicity and familiarity are orthogonal principles. And often you cannot change simplicity. You know, if you've got a complex business requirement, you can try to simplify it, but you know, there's a limit to that. But you can learn things. And I really think that functional code is simpler. There is, I mean, we can see some example at the end. There is less code. It does less. It might put you off if you don't know the language, but you can learn that. And once you get familiar with it, it really becomes easy. So what do I want to do today? There are a lot of really good talks about how to do functional programming in Java. So I can cite a Pragmatist Guide to Functional Geekery by Michał and G after F patterns by Mario, but it's not what I want to do today. Today I want to give you an insight into the theory. I want to simplify the theory so you remember it. I want to interest you so that you want to look more, and hopefully the next time you see an article by Monad like I did, you will feel, okay, I understand. Okay, so this is like little introductions. Now before we go into this journey, it's a bit of a journey, so I hope you all follow with me. We need to establish some notation so we speak the same language. So don't be put off, but this is, I'm borrowing some notation from Haskell, but it's really not complicated. So if I look at this notation here, F, and I use double column, that means definition. So it means I have this object f, which I want to define. And here I say a, arrow, b. So this means it's a function from the type a to the type b. So what is a type? A type, it's like a set. So here my type a is the set of circles, and my type b is the set of squares. And my function f is going to map every element of a, hopefully every, well, it has to b. Okay? So if I use this in practice, I could define a function called parseInt, which goes from string to int. And in Java, we would write it the other way. We would say, well, parseInt, take a string, and returns an int. We're okay with this notation? It's not, you know, it's nothing scary. And how do we do multiple variables? Well, in this case, you just do multiple arrows. So how do you read that? You start at the end, and you say, that's my return type, and everything before that are my arguments. So this add, we know, is a function of 2 integers that returns an integer. And in Java, we do it like that. So if you have, let's say, 5 types, int, 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 it's a function that takes 4 arguments, 4 ints, and return 1 int. Okay? Okay, so now, the next concept is something called function composition. It's fairly straightforward as well. Is that if I have 2 functions, and the first function f that goes from a to b, and the function g goes from b to c, well, I can first call f, and take what I got from f and pass it to g. And doing this in one go is a composition. And this might trip you as well. This is pronounced G after F. So first I apply F, and then I apply G. It might seem the other way around, but if you were writing it as a function like G of F the F, then you would write it in this order. So it kind of makes sense. So if you've got a function F from A to B, then a function G from B to C, G after F is a function that goes from A to C. Now, this is an interesting thing. So this is taken from Haskell. And in Haskell, everything is a function almost. And this operator after is itself a function. It's a function that look at the bracket, it takes two arguments, a function from A to B, a function from B to C, and returns a function from A to C. And this total function is called a higher order function. So I'm going to explain what it is in the next slide. So a normal function, first order, is a classic function, takes some type, returns another type. Now to be a higher order function, you either need to take a function as an argument or return a function or both. So if we look at this function here, times 2, that's the classic function, it just takes a number multiplies by 2. And we could create a function called multiply by that takes a number and gives you a function that then multiplies by this number. So if I call multiply by 2, then I have this function I can keep, and I can keep reusing it. This is a higher order function because it returns a function. Another example, which is both, I could call twice, takes a function f, returns another function, but actually this new function does it twice. So a higher order function is just a function of function, and this is the tool in functional programming that people use to abstract problems. Okay? Sorry. You all with me so far? Yeah, we all speak the same language now. So that was the common language. Now, I think monad needs to be understood in a context. So the context I want to put monad in is something called pure functional programming. So pure functional programming, I like to think as a way of life. It's a philosophy. It's not linked to a specific language. It's just a way of writing code. So what does it mean to be a pure functional programming? Well, it means that your programs is composed of pure functions. So a pure function is a function with no side effect. I'm going to explain side effect. But basically, it means that your function can be memorized, and it always returns the same output for the same input. So your function really is a map. So if you think about the function, let's say times 2, what you could do is you would take your function, and because we know that we have a finite number of integer, you would write your function for every possible, you would run it for every possible integer, you would store the result somewhere in a cache or in the file, and calling your function should be exactly the same as looking it up in a file or in a cache. So it really is like a concept of caching, concept of mappings. So what are side effects? Well, I'm going to cite some examples: modifying a variable, modifying a data structure, setting a field, throwing an exception, printing to the console, doing any sort of I/O. So none of the useful stuff, you can't do it. So of course, there's a trick, because if you write the perfect code that you can't observe, you can't do anything with it, it's useless as a business value. Of course, there are tricks, there are ways around that, but the idea is that the pure functions, they don't do anything of that. And you're trying to use the declarative style instead of the imperative style. So declarative style, you tell the computer what to do. Sorry, imperative, you tell the computer what to do. Declarative, you say what you want. So it's the what and not the how. And this is where the simplicity is reduced, because you have to give less orders, because you don't have to tell the computer how to do it. You just tell what you want. Okay? So this is taken from a book that we call Functional Programming. Some people call it the Red Book. I will mention at the end again. So talking about exception, this is a picture that I took on my way to work. A bit embarrassing. So I don't know if you can see here, but actually it says Microsoft.NET. So of course this could never happen in Java, but we should be careful. So an interesting way to look at exceptions, the exceptions can be seen as a partial function. Why is it a partial function? Because if I have this function f that is defined from A to B, for these two elements it returns a square, but for this given A, it explodes. This is an exception. So it means my function is not really defined. It's partial in its input. And this is bad, because you could see it as a lie. And why is it a lie? Is because I talk about expressiveness in the types. You look at a function that says from A to B. Well, actually, it's not from A to B. It's from A to B for certain A. Please open the Java doc, look inside to find the corner case. No, I want to look at the function, and it says it's a contract. I will give you an A, you will give me a B no matter what. And this is why partial functions are bad. I think if the functions that are non-partial total functions, they're more expressive, they're more predictable, they're more reproducible. Okay, so how do you make a useful program then? Well, the idea is that you have to do side effect, but you're trying to minimize them, and you're trying to put them in a quarantine. So I have this abstract vision of your code from the sky, and the green bit is the good bit, is the pure functional programming bit. And you're trying to make this portion as big as possible, and have all of the nasty stuff at the end. And for instance, you could have one file, let's say your bootstrapping file, your wrapping file, that connects the input, connects the database, connects the output, connects to the screen, input all the network. And this is done only, all of the nasty stuff is done in one place. The rest of the code is pure code and all managed. It's a bit like when you do unit testing. You're trying to if there's something that you don't know how to do, you just, it's a abstract, inject, or mocking, blah, blah, blah. So it's kind of this same idea. Okay, so you have to do side effect, of course, but you're trying to do them only in one place and not spreading the disease throughout your code. All right? So that's the context. Now, we can't talk about Monad yet. First, we need to talk about Functor. So it might seem not related. We'll talk about that. Then we'll put it on the side of our head, and then in the end, we'll bring it to the rescue. So, Functor. Before even explaining what it is, I can let's look at some examples. Well, we know, for instance, I hope you all use optional. Since 2014, you had some time to learn about it. You can create an optional of an integer and say 42. Now, if I create a function toString that goes from integer to toString, I can map my optional, and I get, instead of an optional of integer, I got an optional of string. Interesting. I can do the same, actually, if I have a completable future. There's this static method called completed future. Just create a dummy one that returns 42. That doesn't do any asynchronous thing. But actually, I can also map it. It's not called map, but it's called then apply. I can pass my function, and instead of having a completable future of integer, I've got one of string. OK, so similarity. And now we've got lists. So unfortunately, in Java, you can't map a list directly. You have to first do a stream. Then I can do a map, passing my function. And then I need to go back into the list using the collect. So if you forget about the stream, the option, the completable future, and the map and the list, they all have this notion of mapping, that you've got a container of some sort of type, you pass a function that goes from this type to another one, and you get a container of a different type. So all of these data structures, they're all functors because of that. So let's now look at the definition. So now I'm going to start introducing these little colors, these little marbles. This is just saying this is a type. So this marble is any type you can imagine. It can be string, it can be int, it can be your own object, anything you want. The first job of the functor is to create another type. And this is called lifting the type. If you think about, you take string, you use the optional functor, you've got optional of string. You've got another type now. And here I use this metaphor of the type is in the box. So it's like this idea that the functor is like some sort of container. And when I say container, it's not container at the instance level. So if I say optional of int, I'm not saying that it's the number 4 that's in the container, because if it's an optional, it's 1. If it's a list, it could be, So it's more like the type. The type is in the container. So this is the first job of the functor, but it's not the most interesting. The most interesting is that if we start looking at another type. So I have another type, yellow. Could be anything. I apply my functor, and I've got another type. So now I've got 4 types. Blue, blue in the container, yellow, yellow in the container. But what if I had a function g that can take a blue and return the yellow? Well, my functor must also provide me another function that can do the mapping from the two-box container. And this is done by map. So map, I don't know if it's clear here, but it's a higher order function. And if you look in the code, you do map, you pass it a function. So it takes the function and it creates a new mapping. So the function that creates, and this is called lifting the function. So my function g, that is in the context of the non-functor type, the non-box type, is lifted into the world of the box type. So if we look at those notation from Haskell, we've got f. So here is a functor. So it takes the type A and returns a new type. I have a function g from A to B. So my function map here, so that might confuse you a bit, I will explain. Here I wrote it as a function of 2 arguments. First a function, then a functor of A, and then a function of B. So when I show in the code, map only had 1 argument. Now the reason for that is because Java is an object-oriented language. So you can create a class called optional, and you can write the map function inside that class. But traditionally, this comes from languages that are pure functional, like Haskell. They don't have that. So they have to write map function as a static method. So to get the context of on which optional I'm applying the function, I need the second argument. In Java, this second argument is applied by the this keyword. It's the FA is the optional, for instance, that I'm in right now. Okay, so everyone is okay with this? Why I'm writing it as a double argument? I mean, the two are strictly equivalent. If you use a language like Scala, you can use either. They're exactly the same. It's just a readability. Some people prefer one style or the other. And if I apply map on G, then I have a function from FA to FB for my containers. So, if I had a string int, optional of string, I use the function from string to int, I have optional of int. Okay? So let's look at some implementation of how we would implement map. Well, I've got a function from blue to yellow. And this is interesting because this is 2 examples in functional programming where, because the types are so abstract, there is only one possible implementation that makes sense. So let's look at it. Optional, it's not implemented like this in Java, but you could think of it as like an interface called optional, and then you can have two concrete implementation. Either you have something called sum, so it's just a wrapper that says, yeah, I have this blue, or another one that says, no, I'm empty. So this is called a sum type, but that's if you're interested. And so we need to implement map for these two cases. So in the cases of sum blue, this is very interesting because what do I have? Well, I have a blue. OK, great. And what else do I have? A function that takes a blue to a yellow. The only thing you can do is pass this blue to the yellow. Now I've got a yellow. OK, but I need to return an optional of yellow. So the only thing I can do is put the optional in return a sum of yellow. Now, in the case of empty, I've got nothing. I can't magically produce a yellow. Remember that this is interesting because if I wrote optional, let's say, of integer, you could say, oh, yeah, you could just return, it's possible to implement and say optional of 0. Yes, but I don't know what the yellow is. I don't know if yellow has a 0. So this is an example of where abstracting your type actually massively reduces the number of implementations that are possible. The only thing I can do here is return empty. The only thing that would compile is to return empty. Same for a list. If I have a list of 2 elements, of 2 blues, what can I do? The only thing I can do is apply map on each of the elements and return a new list. And the thing that we observe here is that, this is important, map changes the content of the container, but not the structure. So when I had a sum, I still have a sum. Empty still have an empty. If I have a list of 2 elements, I need to have a list of 2 elements. So the structure is not changed. So just a quick summary about the functor. It's a container for types. We have the function that lifts functions. The lifted functions, it changes the content of the box, but not the box itself. The structure isn't changed. And now, you remember that. Functor is something that has map of some sort. So if you see any sort of class in Java, in Kotlin, in any language you want, and there is a function called map, or a function like then apply and have a similar structure, you know it's a functor. Now, Boromir is getting like, he wants to kick me a bit because this is not the exact definition, but who cares? This is good enough for now. OK, so now you can put monad on the side. Functor on the side. And we can talk about monad. So, monad. So I haven't mentioned, but Bartosz Milewski, he's a mathematician, physician, computer scientist, a very smart guy, and he does a bunch of videos on YouTube, free videos, and blog posts about category theory. I briefly mentioned it's like this mathematical framework that supports functional programming. And he has an article about monad, and he also feels that a lot of people are really confused about monads, and he has a theory to explain his point. And he does a little game. So the game is, can you guess an object based on how you use the object? So it's like a mystery game. So OK, so the first example is you can fix the CO2 scrubbers on board of Apollo 13. So it has to do something with space, probably. Then it can treat wart. OK, so maybe treating space, wart in space, I don't know. Fixing an Apple phone drop call issue. OK, so now it's really getting really confusing. Making a prom dress and building a suspension bridge. So I think probably someone can guess what it is. Duct tape. So, OK, you guessed, but would you think that this is the best way to explain to a 5-year-old what duct tape is? It's not. I mean, you can do millions of things with duct tape, but the best thing is to say, well, you stick things together. And actually, this metaphor is good because it's exactly what monad does, and I hope we can see that later. But the moral of this story is that if you're serious about teaching, explaining monad, it's really stupid to use examples. So we're much smarter here. We're going to use a use case, which is completely different. So the use case is we have a string like this, and we want to, the output of the program is the division of the 2 numbers separated by. So it's a kind of complex problem. And we've heard about this, pure functional programming, we write functions. So let's try to write this in a pure functional programming. So I can see this as a 3-step. The first step is I need to split my string. So I've got 2 strings. Then I need to parse my string. So I've got 2 numbers. And finally, I can take my 2 numbers and I can divide them. Yeah, OK, so let's do that. So this is almost Java code. I am lying a bit here. I'm pretending that in Java, we can write pairs like that. Normally, I will have to use like a pair imported from some libraries. But if I do that, it doesn't fit in the slide. So just pretend that this is a pair. So we've got a split function, takes a string, returns a pair of string. Then we've got a parse function, takes a pair of string, returns a pair of double. And finally, we've got a pair of double, and we get a divide. OK, that's good. And an interesting thing, which is kind of by design, but if we look at the type a bit, So we've got a split function from, let's say, blue to yellow. So blue is string and yellow is pair of string. But we can forget about this. But we kind of realize that actually, yeah, the end of split is the beginning of parse, the type match. And the end of divide is the beginning of parse. Sorry, the end of parse. So we could write this as a one-liner. Our whole program is divide after parse after split. First you split, then you parse, then you divide. And it's great. I mean, not really. The code that we write is pretty bad. Actually, every single function can fail pretty badly. The first one, what if there is no comma? What if there are 2 commas? The second one, what if I don't have numbers? And finally, what if I divide by 0? So this is not, I mean, we can't go home yet. This is just not job done. So we've just said that exceptions are partial functions. It means that currently our program, if you think about a function, it's a function from string to double, but it's partial because if I give there's a lot of strings out there that will make my program fail. So currently our program is a partial function. So we need to fix that. So how do we fix that? Well, one idea is to modify the signatures of the function to change the return type to something called an embellished type. Let me explain. If I've got a function from blue to yellow, I'm going to rewrite the signature of that function to return something of yellow. This is like a wrapper of yellow. I don't really know what this is yet. I'm making no assumption. It's just a different type. And actually, you're already, even without knowing, you're already familiar with this pattern. We talked about exception handling. Well, optional. If you had a function that goes from int to string, you change the signature. Now, actually, I'm going to return an optional of string. And then you can decide if you want to return an optional of or optional empty. And we don't have this in Java, but in other languages, we've got something called the either. Because with the optional, when you say, OK, there was an error, I return optional empty, you kind of lost the context of what happened. So what you would do is you could return something that, so if it's correct, you return the right. If something went wrong, you return the left. And the type of the left is something that you want. It could be an error code. It could be a message. It could even be an exception. But here, I'm not throwing the exception. I'm returning the exception. So that's very different. I'm not interrupting the program. You might also be familiar with asynchronous processing. So if I have this function called sayHello that returns a string, I can rewrite this function to return a completable future of string. And I use something like that. I said that you're not to do logging. You're not allowed to do logging. So how do you do logging? Well, you can, instead of, I've got this method called getMagicNumber. Instead of returning just an integer, so here I'm using the real pair, I will return an integer and a string. And throughout my program, I'm going to build my logging, and at the end, I return everything. And if all my functions are written like that, I can collect all the log in a completely deterministic way. There is no race condition in writing into a file. It's 100% deterministic. And the last one that you might be familiar as well is sometimes you need runtime parameters. So I have this function called buildURL, but I don't really know yet because I need to use some runtime configuration. So instead of returning a string, I can return a function from, let's say, the good old Java properties, the string, and then use a lambda, and I can build my URL using that lambda, and then at the end, I can just return it like that. So this is to show you that you're already used to this pattern of changing the signature of a function to fix some sort of problem. Okay? So let's try to fix our beautiful program by using optional. So I'm going to rewrite it. So now the split function returns optional of pair. The parse function returns optional of double. And the divide function returns optional of double. OK? So be ready. We can write this beautiful piece of code. Let me take you through it. So we call split. That's an optional. So if split is present, I pass it to parse with the get. I get an optional. If parse is present, I pass it to divide with the get. I get another result. If result is present, I return get. Otherwise, returns empty. And as far as I'm concerned, that's victory, because here we are, this is like we wrote, this code is 100% fail-safe. It's now a non-partial function. It's a total function. This code is unbeatable. So, here we, honest Java programmers, we're happy. Now, I don't know how many functional programmers you know. There's always like one in the family usually. There's one thing you should know about them is that they're extremely greedy. And why are they greedy? Is that while we're celebrating going home, they're like, they're grumpy, they're not happy. So let's give them the benefit of the doubt to try to understand why are they unhappy. Well, because we kind of messed up their types a bit. Now, if I look at the types, well, that doesn't match. And that doesn't match. So where is my one-liner? I can't do that anymore because the types don't match. So this is kind of why now, we don't have to do that. The code that we wrote is perfectly functional. We don't have to try to have the cherry on top of the cake of having this one-liner. But let's see, if we wanted to, let's see how it could be. So if we summarize the problem, is that I have a first function that takes a blue and returns this thing of yellow, and then I have got another function that takes a yellow and returns the same thing of orange. The types don't match, but I still want to compose them. So to compose them, we can define this new operator. Well, the formal name is this is called a Kleisli arrow, but some people thought it looked like a fish, or they call it the fish operator. That is not my invention. I promise people call it like that. And this is like the after operator, the composition, except it's smarter because the type don't match, but somehow that thing can open that. I mean, I don't know if it can be open, but it does something. It managed to extract the yellow, and it continues. So if we look at the type, if we've got a function f from a to m, so m is my mystery thing here of b, and a function b from from b to that m of c. If I do this g after f with the fish, I get a function from a to this wrapper of c. I bypass the middle thing. So that's the big question. How do we compose those wrap type? And this is now you're like, hey, Cesar, you just told us about Functor. Can we use the Functor? Because so far I had made 0 assumptions. So now remember that this weird shape thing is the type that we use to change the signature. So now let's say, okay, we can't take any type. Let's just take those that are Functor. Let's take the type that have a map. Okay, so let's do that. So we start again. Now we have a function from blue to yellow in the box. I still have a function g that goes from yellow to orange in the box. Now, the next, if I press, you might be a bit confused. So I will take it slow. Remember what map does. Map, it opens the box, takes what's inside the box, give it to a function, take blindly what the function returns, and put it back in the box. Well, my function g returns a box. It means I have a box in a box. The outer box, it was there all along because it's there. And the inner box is because, well, that's what I had. Okay. So this operation is map g after f. I do f, and then I do map g. So if we look at the type, we've got our types, and if I do map g after f, I've got a function that goes from a to mmc. And what I really wanted at the end, I wanted to do something that goes from a to mc. So we kind of like there, but not really. And the idea is that we want something that can reduce these unnecessary levels of boxes. And once I was doing this talk with in a French group, and I said, "Oh, it's like Tupperwares when you put your leftover in the fridge. There's no point putting in 2 Tupperwares." And someone said, "Yeah, but what if it's a smelly cheese?" So unless it's a smelly cheese, only 1 Tupperware is enough for your leftover. So we want to get rid of this unnecessary bit. So okay. So we said, okay, our type must be Functor, so they must have a map function. Let's add an additional requirement. Let's say that our type must also have this function called flatten. And flatten is something that just takes 2 types, so for instance, optional or optional, and returns just 1 optional. Okay, so now let's start the whole journey again. We start from blue, we apply f. Okay, so then we apply map of g. I have yellow in 2 Tupperwares, and I remove the unnecessary one. And I look at the type and it's like, yeah, so flatten after map g after f, first f, then map, then flatten. And I found the fish. This is what we were looking for at the beginning. If I look at the type, it's exactly that. So the fish operator, oops, sorry. Sorry about that. The fish operator is just doing this map and then flatten. And this is what a monad is. The first definition is a monad is a functor that has flattened. So Boromir is getting really upset here because this is not a mathematically sound definition, but you can remember that. Actually, there is a better definition coming after, so you can even forget this one if you want. So that's what a monad is. Map and flatten. So if we look again at this, just the map and flatten, well, some people decided to give it a name, flat map. It's just the action of doing a map and then doing a flatten. And if I look at a type M, so that's my container, and my function f, if I do, so I remind you, the signature of map, it takes a function from A to B, and it goes from MA to MB. And now flat map is almost the same, except that the function that it takes now, it's M of B. So if you're wondering to know about should I use map or flat map, well, in the context of optional, if you have a function that you know cannot fail, that returns from type A to type B, then you know you can use map. If you have a function that potentially can fail, let's say from type A to optional B, then you can use a flat map. And of course, depending on which monad you're looking at, because yeah, optional is a monad, that's why, because it has flat map, it has different meaning. But basically, the signature is different, okay? And the fish operator is just flat map. So if we look at, you might be wondering, what's the difference between the fish operator and flat map? Well, let's just come back to the add function again. So add function, remember it takes 2 int, returns another int, but as a human, we prefer writing plus. We write a plus b, and the compiler rewrites this as add ab. So the plus is like add. It's not exactly the same, but it corresponds. And actually, the same is between the fish operator and flat map. The fish operator is just doing a flat map the other way. So the fish operator is the operator for flat map. And if I look at my types again, well, even though the types don't match, I can still say divide after fish, parse, after fish, split. So first I do a split, flat map parse, flat map divide. And that is the definition of a monad. A monad is something that has flat map. Again, that's not mathematically sound, but as far as you're concerned, this is all you need to remember. If you see something with a flat map, it is a monad. And it's not difficult. I mean, you've used flat map on the list. You've used flat map on optional maybe, or maybe not. Because every time I do this talk, people tell me, I've been using optional for years, and I didn't know it had flat map. And you will see how to use it in a second. So just to summarize, the monads that you already know optional, you already know either. You might already know computable future and probably logging, not really, and maybe environment as well. So to make Boromir a little happy, I feel bad. I put that slide in. Just wanted to highlight, there's another similarity between future optional and stream, let's say. Computable future has this static method that takes a number and put it into a future. And optional has this of method that takes, sorry, not a number, anything, a type T, and put it into, and the same for optional. And stream has that as well. So this is another, so if you look at, so the first requirement for a monad is to have flat map, and it also needs to have this pure function, and it's just, sorry, it's here, it's just something that takes a type and put it into the container. Because remember, a monad is a functor, so it is a container of type. Okay. So monad definition. It's a functor with flatten, or it has flat map. What are the advantages? It can manage and control side effect. Remember, the whole reason we did that is because we had a program with side effect. We said, okay, we want to fix it. And that's, the next one is program with side effect as if they're not here. And that is the cherry on top of the cake that the functional programmers were asking about. Because we're going to see in a second that your monad takes care of your side effect, but you don't even see it because the flat map does the work for you. So the monad makes partial function total, and you can compose function with side effect using flat map. So remember, this was our beautiful code. We used optional, and we didn't know the optional was a monad. And now we know optional is a monad, so it has flat map. Boom. This is so much simpler. I split. Split is an optional. I can call flat map. I have access to the inside. I give it to parse. There's a monad. Flat map. Boom, boom, done. And this code is really efficient because remember that flat map uses map. And remember that map on empty, optional empty, does nothing. So if there was an error at the beginning on my split, this lambda does not get called. If you look at the implementation of optional in Java, if you have IntelliJ or any sort of IDE, you can click inside of monad. It's implemented in Java, and you will see there's a case. It says if present, do that, otherwise return empty. The lambda is not even called. So it's very efficient. And also it's very small. And this is a cherry on top of the cake. It looks like here we're doing sequential programming, and we are. But there is something that happens for us behind the scene, which is the handling of this. In the case of optional, it handles exception. If I used future, so future is not called flat map, it's called and then. It would be this, and then, and then, and then. And I don't have to manually wait for the first future to finish and then pass it. It just does it for me. Okay, so I kind of feel bad though, because I've been saying things about functional programmers. And I feel bad because I didn't give you a full picture. On top of being greedy, they're also hypocrites. And why are they hypocrites? As I remember that we said that they love the declarative language. And there is a joke going on. They said that Haskell, which is the god of functional programming, is the best imperative language. It's like, why? So I don't want to show you in Haskell because this might scare you, but I can show you in Scala, because Scala is quite close, it's quite similar to Java. So in Scala, a function, you just put the def keyword on top of it, and the return type is at the end, and option null is called option. So it's the same. We've got a split function that takes a string, return option of string. A parse takes a pair of string, returns option of double, and divide takes a pair of double, return option of double. And now here is the hypocrisy coming. This is called a for comprehension. Look how it looks. You just create, so in Scala, you just say for, and then you say, okay, split, this arrow the other way equals the function split. So if this was an equal sign, if I say split equals calling my function split of s, the type of split would be an optional. But you can see that I take that variable split and I pass it to the next function, parse. Parse doesn't take an optional. It takes a normal pair. So behind the scene, the compiler is rewriting this as a bunch of flat map, flat map, flat map. And at the end, I just return. And this is really the cherry on top of the cake, is that I have this code that completely handles side effect. I don't even know about it. If you forget how it works, it's kind of, oh, yeah, split equals split, parse equals parse, divide, divide. And I don't even know that actually my code handles any sort of error. So that is the cherry on top of the cake and the hypocrisy and the greediness of functional programmers. So something I've tried to say during this talk, and I want to say it again, I have this little diagram here that summarizes two states. On the horizontal axis, whether we manage side effects or not, and on the vertical axis, whether we can compose our code or not. And we started here. We had a program that could write as a one-liner, but it was unsafe. It didn't manage side effects. So what we did is we used the wrapper type to move on the opposite side of the quadrant to get a program that managed side effect that is not composable. And we could have stopped here. But if you're greedy, you can use Monad to have the cherry on top of the cake, which is in the composable state and manage side effect. So that's important to understand that Monad doesn't solve a problem that you have to solve. It just makes your life easier. So I think that's why, as a developer, we should use them. They make our code easy to understand. Once you know what flatmap is, so simple. So what are the key takeaways? Functor is something that has map. Monad is something that has flat map. This is not exactly accurate. If you want to know more about Monad, now you can search about it and you can find there are additional requirements to qualify to get the certification of a monad. Now, if you want to change the return type to manage side effect, choose a monad. You don't have to, but if you choose a monad, you're going to get this flat map for free. Oh, sorry, I just remembered I forgot to say something about the for comprehension in Scala. The Scala language, some libraries in Scala, understand what a monad is. So if you write your own data structure that happens to be a monad, if you were to write your own super fast list implementation, list is a monad, you can tell Scala, hey, this is a monad, and automatically you can use this for comprehension. So you get this like really nice things like that. And finally, yeah, monad allow composition of wrapper types, data types, using the fish operator. So before you go, my advice is be pragmatic. Don't try, oh yeah, tomorrow I will write 100% pure functional code in Java. Don't. Like, Java is not meant for that, and I'm not saying you should. I'm just saying you know what can be done, and basically keep an eye out. Now that you know that you have this concept of monad, and you know how to recognize a monad, next time you see a data structure, do dot, explore the function. If you see a flat map, you know it's monad. Maybe it's going to be hidden like and then or something like this, but you know that what this monad does. Don't try. There's no point to be 100% pure in Java. It's not what it's for. But you can use the tools that are already there, and maybe in the next release of Java, there's going to be more stuff like this coming, and now you know what to look for. So if someone could come to this talk and you want to give them a 5-second definition of what a monad is, you can just tell them a monad is the cherry on top of the cake that's actually a fish. So some sources, I mentioned Bartosz Milewski. If you're interested if you kind of like math and want to understand what a monad is, because the monad is defined in an abstract context, not even related to functional programming. That's interesting. You can look up Bartosz Milewski, category theory for programmers, really good. If you want to learn about pure functional programming, there's the Red Book, Functional Programming. It's a book about pure functional programming in Scala. It doesn't teach you Scala on purpose. It kind of does along the way. And I put some, I didn't mention that, but a talk from Brian Goetz at the Java Language Summit when he talks about the potential idea for functional pattern matching in Java. And this is kind of saying there are people already looking at how can we make Java more functional. and The Art of Simplicity by Venkat, if you want to check this out. Very interesting talk. And I want to say thank you to Bartosz Milewski. I don't really know him, but he puts all this good stuff online. Georgiana, who is a math PhD, who was, first time I did this talk, she was correcting some of my assumptions, so then she helped me be more accurate. And my friend Julien, who is very good in functional programming and has helped me in this journey of being more functional. And if you've got questions, I'm happy to answer them. You can also find me on Twitter. And thank you very much.
Cool. So do we have any questions? If you could wait for Alex to pass you the mic if you do.
Do you all know what a monad is now? Yeah? Kind of?
Hi there. I was wondering if you wanted to say a little bit about what you program for a living.
Yep.
So who do you work for? Is this a style you use every day?
Okay, so I work for a company called Convendia. We're a small startup. So my main language is Java. So actually, just Gemma was saying, we've started. So we have microservices architecture. So every time we start a new service, we try new stuff, and we try Kotlin. Amazing, really simple. I mean, we were on Java in Spring. So easy to move to Kotlin, and you get a lot of functional stuff for free. Actually, monads are baked into Kotlin because you can't have. So in Kotlin, you can't. So if you have a string, it can't be null. You have to say this type is a nullable, and actually what it is, it becomes an option. You don't really know, but it's an option, and it's a monad. So you can do this one-liner. You start with something that could be null, and you do question mark dot, and you can do all of this. Behind the scene, it's exactly like a flat map. And it has all of the, for example, the lists are monads, because in Java, lists are not monads. You need to go to stream, do the flat map, the map, and then you need to go back to list. Very tiring, and you can only go through the stream once. In Kotlin, all of the collections have map, flat map, fold, any sort of functional stuff that you need. So yeah, so that's kind of like, I mean, I don't really do pure functional programming for work. On the side, I do because I like it, but yeah. But personally, I think knowing what's out there has helped me write better Java code, because it had forced me to be aware of, oh, actually, what's there in Java, and maybe it only has a small portion of the the pure functional, the functional stuff, but what's there, use it. Every time I've done this talk, I had people come to me, I've been using optional, like you showed, with if present. Never use if present. You probably 1 in 100 you need to actually use if present. Most of the time you can use flat map.
There were two things. One, your slide right at the beginning, where you talked about best practice.
Yeah.
That would apply, I think, to any Java development.
So which best practice? The advantage of pure, functional programming?
It's about your third slide. It's,
okay.
Use immutable types, have no side effects.
Yeah. Yes.
If you read Bob Martin's book, that's pretty much what he's been talking about for years.
This one?
Yes.
Yes.
The other one was, have you used Project Reactor and the reactive stuff?
Yes, yeah. So yes, yeah. Actually, something I wanted to mention in the hype of functional programming is the reactive programming, and it's kind of like on top of pure functional programming. And I have, yeah. I mean, I use the Spring one. So one of our microservice, it's a notification service, and it's where we try to give it a go. It's quite nice. It can be tricky for testing, because everything is unobservable, so you have to be careful. You create something, and then you forgot to observe it, and you're like, why isn't it working? Or you observe it twice, and you're like, why is it doing it twice? So once you get around those little things, I find it quite nice. I mean, yeah, the functional stuff is the grammar for all of this reacting stuff. You all the flat map, the mapping, or something like that. Yeah.
Mm-hmm. And yeah, the last point was that when using the fluent style that you've used for the flat map,
yeah,
debugging is a nightmare.
Yes, so that's why, so that's completely true. One way around that is trying to keep your function simple. Don't try to write a chain of 50 flat map, trying to keep functions that do a very simple things. And if you do that, I mean, if you've got small functions with the quite restricted types, there's so much that you can get wrong. And actually, one of my friends, actually, who I mentioned at the end, Julien, at the end of the in London, there's like a conference called Lambdale. It's like a Lambda functional programming conference in the pub, and he's doing a talk about, it's called type versus test, and he talks about how to restrict your types of your function to make your function impossible or less likely to get wrong. So if you've got a function from string to string, probably you're not expecting every string. So maybe you want something from a set of names or day of the week, and actually you could say, well, let me create a data structure like an enum, or it's called an ADT, but in Kotlin it's called a SIL class, in Java it's called a case class, that you only said, I can only get these things. And by restricting your data type, by making your function smaller, you make debugging a bit easier. But yeah, that's a fair point, that if you've got map, flat map, this becomes a bit easier. But in IntelliJ, I don't know, are you using IntelliJ?
No.
Because you can, so when you put a breakpoint, it will ask you, do you want to break at the line, or do you want to break inside the lambda, so you can do little things like that. But yeah, fair point.
Yes.
Okie dokie. If we've got no more questions, let's have one more round of applause for Cesar.
Thank you very much.
So I think we're going to decamp to the William IV pub, which is if you come out the front doors of the office, head down the hill, and it's the first pub you come to on the right-hand side of the road. I'm sure someone will let you follow them if you've never been before. So thank you very much for coming, and we hope to see you again soon at another Brighton Java.